I'm Johannes Schumann. I'm PhD student at Erlangen, and I'm working on KM3NeT. So that's the reason why I'm presenting you the Python software environment in KM3NeT. And so first, I will give you an overview about KM3NeT. So it's a water Cherenkov detector infrastructure in the Mediterranean Sea. At the moment, we are focusing on two sites, which is Orca. It's the more dense instrumented detector for tackling the lower energy and determining the neutrino mass hierarchy. And we have ARCA, the name-giving side. It's more sparsely instrumented, but it has an in its final configuration, it has an instrumented volume about 1 cubic kilometer. And this is for discovering high energetic astrophysical sources. And so we're building those at the bottom of the sea. So it's a challenging task to build up, operate, and scientifically exploit the detector. And I think with respect to the data handling and the computation, is the challenge is to minimize the obstacles to access data from multiple languages and platforms, and in order to maximize the information from the data we take. To the detector setup, I've given you here. So basically, how this works out. So we have our sources. As I said, for the lower energy branch, we're using atmospheric neutrinos, and for the higher energies, it's we are looking for active galactic nuclei or also supernova. Then when the neutrinos propagate through Earth, we are looking for the Cherenkov light of the secondaries for neutrino interaction. And you see here an artist impression of the Orca detector and its final configuration. So the Orca detector will look mostly the same. So they're sharing the same technology with optical modules, but here the measures are for Orca. So for the computational setup, we have here on the top left, you see here the detector. It's connected via an undersea cable to a shore station. And then our main software for running the whole detector is written in C++. So we have there a tier-based processing chain and do the data write out to the computing center. And what I've given you here is the Python environment there. So we can access the data, the written out data from our file format, which is in root, and for example, from the database with those tools. And we have also a large tool set for this, for specifically for KM3NeT in Python. So for the C++ side, as this is used for the triggering, calibration, or reconstruction, this was the first thing we had for Python. So the classics, the usage in Python via PyRoot and CPy. And there we had at a very early stage the focus on using it from Python and developed it that way. And when we have a look at a small coding example here, then we can do here the import with what is called AA, that's the framework name. I've taken one file from a package which is called KM3NeT test data, where we have all our examples for all our data formats available in order to use it for unit testing, or in this case, to give an example how the reading is done. Then you can just open an event file and dump out the data. So as I said, it's was already a focus there on the easy usage. But in all, the problem there is a little bit that you need to have still root installed. And as we have such a nice thing like Uproot, we came to the package called KM3 So we have now the possibility to access our root-based data via Uproot and Awkward. And here we have mainly two file formats, which are called internally online and offline. So one file format is for the detector DAQ write-out, and we have the offline file format, which is for the Monte Carlo simulation data and the final event reconstructions. So as I already said, the reading of the data was previously possible, but you need to have root installed. And from our benchmarking we did on this, the PyRoot was slower and required more memory than doing it with Uproot. And we also have internally an optimized iterator behavior to allow this lazy readings of multiple branches. And the last point, that's more, I think this uneven data structure of because we have per event a different number of photosensor readings, what we call hits. That's in the HEP community, nothing too new. In the astronomy groups, that's not that common because there also a lot of applications have images with a fixed resolution where you can just then use multi-dimensional arrays. So this fits for us also perfect with the awkward package. And to also go in the code there, let's have a look at the Uproot perspective. When I open a file with Uproot and do just a show on the root path in the file, then you see that there are a lot of custom structures in this file, which Uproot can handle really good from the start on. So if we then go to the hit information, for example, then I can browse via the path to this branch, and I have here all the keys given in there. And as we use general purpose classes, for example, for the DAG readout and the simulation, there are also fields which are given there, which are just empty for this example file because I've taken it from simulation. So, for example, here the amplitude we get from a photo multiplier, or the pure time without calibration should not be displayed. And yeah, and we should keep that in mind when we have a look with it with KM3 but first, I just want to prove that the access of the data is possible. So I have here a very, very short example. So when I go in the file just with Uproot, then I can read the events, browse to the channel ID, and print out the information. Oh, I see. I think I messed here something up, but I will. Oh, that confuses me. Okay, I think maybe we can talk about this at the end. From the KM3 perspective, then I already told about this naming we internally have. I take such an offline file reader, and then I can also access the fields. And when I then print out the fields, then you see that these fields I've talked about 2 slides ago, like the amplitude or the pure amplitude, is not given here because it's from a simulation file. And then again here I can access the data as I told, as I did it also for Uproot, or I tried to. Yeah. from that on, we have access to the data. I also want to talk about KM3 pipe in order to process the data in a way. So KM3 is a multi-purpose framework based on the pipe project, and as the name says, um, this is focuses on pipeline workflow. So the all interoperability functions to all relevant detector interfaces or information are provided by utilizing also other KM3 pipe packages like KM3IO. So we can use their detector data in the formats we have, and also we can use their directly DIQ, the DIQ network interface to process live data from the detector or also from the database. Inside the package, we also, or the package is able to convert data to HDF5. So we can convert here from different file formats, and this makes it also possible to read it easier from other platforms where you don't have root access, for example. We also have benchmarking there, and we have functionalities for high performance computing, so we directly can submit our scripts to, for example, the talk interface for batch processing. And we have a built-in provenance tracking. So going again to an example for that. So this is basically all you have to do to set up a pipeline. So you create a pipeline instance, and then you attach the modules you want to use. So in this case, I start with an event pump for reading the event files. I've added a status bar to get some feedback of the status of the processing, a calibration of the data, and then I have two custom modules. I will show them on next slide. And then in the end, this all is written out by an HDF5 sync to an HDF5 file. So I've taken two custom modules there because you have in principle two possibilities to work with the data or process the data with your modules. So if you don't need an internal state, you can just pass there and function, which I have here. So you get then from the pipeline one blob where the data is in, and you can access this data, can do your operation. In principle, you can also then store data in the blob to then, for example, store it in the HDF5 file in the end, and then afterwards to send the data to the next module, you return the blob. If you need an inner state, then you can also do it by a class which is derived from this KM3 pipe module. And here you have at the beginning this configure method, and in the end the finish. And for the actual processing, you have this process which is then is then equal to doing it by a function, just with the advantage that you have access to the inner state of your class. So in the end, you have to run this all. So you just do a pipe drain, and then the data is so the pipeline is then executed, and you see here the output of the function for how many hits are in the single event, and for this event or for this hit statistics module, here you get the mean number. Okay, that was something on the workflow, but we also do simulation in the with Python, and there I want to give you an overview about. Oh, I forgot the provenance tracking. Sorry for that. You can in KM3 pipe, you can also get easily access to all the information of how your data was created by access this provenance field. And this contains all versions of modules or packages you used in there, and this is then printed out here. I have you can access this as in multiple formats. I selected here JSON, and now we come to a simulation package, which is called KM3 So for simulating neutrino events, you have to use or we use neutrino generators, and Gibo is one of them. And the overview about Gibo, it has an factorized model. So the primary interaction is done via neutrino interaction, and the nucleus is modeled as via a relativistic Fermi gas with superpotentials. And the final state interactions are done via propagating of phase-based densities using the Boltzmann-Uhling-Uhlenbeck equation. And the problem with that, the Gibo itself is written in Fortran, and we were in contact with the Gibo group to check out how we can utilize this package for KM3NeT. And it turned out that it's very difficult to not to use it in their idea of the workflow. So you have to use it as this monolithic application with the data right out to files, and then you have to convert the files. So in order to do this, this is a Python-based wrapper, which uses then Gibo inside of a container, which we distribute by the KM3 in the Docker container. And with KM3 the conversion from the bare neutrino interaction is done to the KM3NeT data format. So how is this done? So first, you have to set up a neutrino job card, which is basically the GiBUU workflow. And here you generate this job card by the basic information about the energy, what target, what interaction type, what flavor. And then you just call this run job card and give it a directory where the data should be written to. And if that has finished, then you can just by this GiBUU output object, which is provided by KM3, you can parse this data. And for example, if you just want to really use just the GiBUU data without any detector specifics, then you can just return it, for example, as an pandas data frame and access the information in there. Or to get really the simulation file, in this case a KM3NeT specific simulation file. Here I have a single method which writes out this or which converts this data to an KM3NeT file. And when you just have to provide a few informations there. So basically this GiBUU output object and the geometry of the volume where the interaction should be placed. So we have the detector, and then basically can volume around it where the interaction can take place. And in the end, there's also in KM3 proposal. The proposal package is utilized to propagate tau leptons and to decay them. So when we now use this function, then you can see, okay, you can the example see here. And then we can just again use KM3IO to read this data, and you see that this is then a normal KM3NeT file, which then can be used for further processing in our simulation chain. So, okay. last project I want to give you an example, or want to show you here, is the KM3 Services package. And this is this provides a microservices API for different functionalities, or for example, for calculating oscillation probabilities. Here on the right, you can see how this all works. We have this, the communication is done via REST API and JSON format, and the whole microservice is then running in a Docker container, converting the information from the REST API to NumPy arrays, and then calling the specific library, in this case, osprop for neutrino oscillation probabilities. This Docker container with this services can run locally. It can run on your own server, or it can be run on our server. So this is very flexible there. And here you have an example how the application works. So in this case, for oscillation probabilities, we set up this oscillation probability object. We give the basic information, so the number of bins, or in this case then energies, the cosine angle from the detector point of view, and then the PDG IDs of the neutrino types. And then we just call here oscillation probabilities for, in this case, the transition from electron neutrinos to all to the other types. And then you see here that this is the expected result for the oscillation probabilities. Yes, so here is an overview about the packages I had not the time to tell you more about. So we have also packages for the for accessing our Oracle database, which stores basically all information about detector hardware, calibration, monitoring, etc. We also have for KM3 Flux for parsing flux tables, also with interpolation functionality. KM3 Astro is an extension for AstroPy for coordinate transfer or celestial coordinate transformations, with focus on the detector position. This package I've already used in the code. We have there in KM3NeT test data. We have a collection of all kinds of data formats we use for unit testing, for example. And Rainbow Alga, we have there also an GUI for animating events in the and the light distribution in the detector. So with that, I come to my summary. So the KM3 Pi collection provides high compatibility with all interfaces of the detector. So the challenge I've mentioned at the beginning of the obstacles, for reducing the obstacles to access the data, I think for Python we have taken this, or we have solved this. The focus here is on data monitoring, pipelines, and provenance, and also with the aspect that we had from the beginning, the PyRoot bindings, and then now we have this large collection. This all is widely used in tools and scripts in KM3NeT, and most of the packages are open source and distributed via PyPy. And as I saw that there's tomorrow also a session on Julia, in KM3NeT we are also working on Julia packages. So we have already in KM3NeT an existing framework called NERCA.jl. We have there a real-time event reconstruction for high-level detector monitoring, which is then used in the KM3 Mon, also our monitoring tool we use. And there are also general high-energy physics Julia projects, which originate from KM3 members. So, for example, Uproot, which should provide or provides native root file reading. It's at a very early stage, not with so much features as Uproot, but we're on the way. And corpuscles is a particle property lookup and PDGID lookup package. And for neutrino oscillation probabilities, we have neutrino.jl. And with that, I would say thank you for your attention.
Thank you very much, Johannes. Very nice, very complete overview. And you have quite a few, well, a good handful of questions coming through on Slido. Are you able to share?
Yeah, I think I've shared my whole screen, so I think, can you see my browser now?
Perfect, yeah, see that well.
So, where we start, I think I start from the bottom because they have prepared something. The monitoring system is pure Python with a little bit of Julia, and I can show you something there. Here I have the our monitoring page, and it's a little bit small. Here you can see this Julia event reconstruction. So that's not publicly available because that's all preliminary data. So I just show it here. But here you can see this live interaction, or we have also for monitoring to see what the status of the detector is. We have here all the triggering. And as I said, all Python with a little bit of Julia. So I hope this is okay. Okay. How do you package and deploy all different pieces of KM3NeT specific code? I don't know. We have all this specific code. We have the Docker CI. We have most of them, as I said, on distributed via PyPy. So basically, if you are working on this, you can just do a pip install. So we have also our publicly available GitHub profile, and the link you can find in the on the agenda. I added it to to my contribution, so maybe you want to check it out. And I hope this answers the question. To Jim, yes, the Julia session tomorrow, I already planned to be there, so I don't want to miss it. Do you have a sense for how newcomers find has it changed as you use Python more? How to answer that? So I think for this wider range, I think that's better for newcomers, because actually what you can do with C++ or Python, I think that's it's with Python it's an easier start than with Root, but I think it basically comes to what you're familiar with. So if you're basically an expert on C++, and as I said in the beginning, there or we had at the early stage already this Python binding. So I think from my point of view, I maybe don't have the experience now, the overview. I think I cannot answer this, but in general, I think it's more easy with this all Python possibilities. How much interaction is there with KM3NeT software development and other similar experiments, example ice group? I'm not really too familiar with the whole software in IceCube. So we have considered using IceTray, but I'm not really sure about now. So we're basically using now our own software.